not in-flight pit insertion. Neither of these effects is likely with implosion weapons, since there is normally insufficient fissile material to form a critical mass without the correct detonation of the lenses. However, the earliest implosion weapons had pits so close to criticality that accidental detonation with some nuclear yield was a concern. On the 9th of August, 1945, Fat Man was loaded onto its airplane fully assembled, but later, when levitated pits made our space between the pit and the tamper, it was feasible to use in-flight pit insertion. The bomber would take off with no fissile material in the bomb. Some older implosion-type weapons, such as the US Mark IV and Mark V, used this system. In-flight pit insertion will not work with a hollow pit in contact with its tamper. Steel ball safety method. As shown in the diagram above, one method used to decrease the likelihood of accidental detonation employed metal balls. The balls were emptied into the pit. This prevented detonation by increasing the density of the hollow pit, thereby preventing symmetrical implosion in the event of an accident. This design was used in the green grass weapon, also known as the interim negating weapon, which was used in the violet clue and yellow sun Mk.1 bombs. Chain safe tie method. Alternatively, the pit can be saved by having its normally hollow core filled with an inert material such as a fine metal chain, possibly made of cadmium to absorb neutrons. While the chain is in the center of the pit cannot be compressed into an appropriate shape to fission. When the weapon is to be armed, the chain is removed. Similarly, although a serious fire could detonate the explosives, destroying the pit and spreading plutonium to contaminate the surroundings, as has happened in several weapons accidents, it could not cause a nuclear explosion. 1 point safety. While the firing of one detonator out of many will not cause a hollow pit to go critical, especially a low-mass hollow pit that requires boosting, the introduction of two-point implosion systems made that possibility a real concern. In a two-point system, if one detonator fires, one entire hemisphere of the pit will implode as designed. The high explosive charge surrounding the other hemisphere will explode progressively, from the equator toward the opposite pole. Ideally, this will pinch the equator and squeeze the second hemisphere away from the first like toothpaste in a tube. By the time the explosion envelops it, its implosion will be separated both in time and space from the implosion of the first hemisphere. The resulting dumbbell shape, with each end reaching maximum density at a different time, may not become critical. It is not possible to tell on the drawing board how this will play out. Nor is it possible using a dummy pit of U-238 and high-speed X-ray cameras, although such tests are helpful. For final determination, a test needs to be made with real fissile material. Consequently, starting in 1957, a year after Swan, both labs began one-point safety tests. Out of 25 one-point safety tests conducted in 1957 and 1958, 7 had zero or slight nuclear yield success, 3 had high yields of 300 T to 500 T, severe failure, and the rest had unacceptable yields between those extremes. Of particular concern was Livermore's W47, which generated unacceptably high yields in one-point testing. To prevent an accidental detonation, Livermore decided to use mechanical safing on the W47. The wire safety scheme described below was the result. When testing resumed in 1961, and continued for 3 decades, there was sufficient time to make all warhead assigns inherently one-point safe, without need for mechanical safing. Wire safety method. In the last test before the 1958 moratorium, the W47 warhead for the Polaris SLBM was found to not be one-point safe, producing an unacceptably high nuclear yield of 400 pound, 180 kilograms, of TNT equivalent, hard-tack titania. With the test moratorium in force, there was no way to refine the design and make it inherently 1-point safe. A solution was devised consisting of a boron-coated wire inserted into the weapon's hollow pit at manufacture. The warhead was armed by withdrawing the wire onto a spool driven by an electric motor. Once withdrawn, the wire could not be reinserted. 78. The wire had a tendency to become brittle during storage and break or get stuck during arming, preventing complete removal and rendering the warhead a duck. 79. It was estimated that 50–75% of warheads would fail. This required a complete rebuild of all W-47 primaries. 80. The oil used for lubricating the wire also promoted corrosion of the pit. 81. Strong link forward/weak link. Under the strong link forward/weak link system, weak links are constructed between critical nuclear weapon components, the hard links. In the event of an accident, the weak links are designed to fail first in a manner that precludes energy transfer between them. Then, if a hard link fails in a manner that transfers or releases energy can't be transferred into other weapon systems, potentially starting a nuclear detonation. Hard links are usually critical weapon components that have been hardened to survive extreme environments, while weak links can be both components deliberately inserted into the system to act as a weak link and critical nuclear components that can fail predictably. An example of a weak link would be an electrical connector that contains electrical wires made from a low melting point alloy. During a fire, those wires would melt, breaking any electrical connection. Permissive action link. A permissive action link is an access control device designed to prevent unauthorized use of nuclear weapons. Early PALs were simple electromechanical switches and have evolved into complex arming systems that include integrated yield control options, lockout devices and anti-tamper devices. References. Notes. The physics package is the nuclear explosive module inside the bomb casing, missile warhead, or artillery shell, etc., which delivers the weapon to its target. While photographs of weapon casings are common, photographs of the physics package are quite rare, even for the oldest and crudest nuclear weapons.